Hello, this is a supplemental video to the video that we had made before having to do with lab number 11. I know in lab number 11 video, a number of the things I was pointing at, the cursor didn't show up. But what I want to do here is I want to show you how to take the data, because I think that was confusing some people. Now, in my case, what I did was I printed out this sheet here, with the spectra on it, from the historical paper. I'd also included a PDF, that's what you can print out, or what you can do is work on the PDF itself if you'd rather. It's up to you depending whether your printer is working compared to a good PDF viewer. And of course, GIMP will open PDFs and they'll also allow you to measure things on the screen if you need to. I also printed out, so I would have it to show you, the part of the spreadsheet with the calibration data. These are the reference wavelengths of all of the wavelengths on the calibration part of the spectrum. These are their names, and these are where you fill in the actual distance they are from a reference point. The goal of the calibration part is for each of these lines here, that is from gas discharge tubes. And remember, dark is light and light is dark. So each of these lines should be wavelengths that we know what they are. And they're either hydrogen or they're helium from an associated discharge tube. It turns out that these two lines here are calcium. And I discussed these before with you, but I might not have been able to point very well. So this line here and that line there are both absorption lines, and they're the calcium lines because they're kind of easy to see and understand what they are. Now, here are the calcium lines in this spectrum. And you can see here they are in this one, and this one, and this one, and this one. And you can see the circles circled them on top of it. And the circles are color-coded based on the color you would see them as. Of course, you don't see the color in my black and white printout. So let's first get a sense of which one of these wavelengths correspond to which one of these lines. So notice that on the far right are longer wavelengths, more to the red, and the far left are shorter wavelengths. And so, for example, helium and H zeta lines, this is at about 389, are the thick two lines that are merged. And that's the shortest one we have. So these are clearly this one here. So I can label that. And I decided to label it with a little 2, just simply because it was in box 2. You can label it however you want. You can label it here, you can label it here. Either way works. Well, now I'm going to count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9. I see 9 there. And here I have a reference sheet with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Which means that one of these lines that are on my reference sheet must not be on this top chart here, or at least not be very visible on that top chart there. However, if you look closely and you look at some of these other ones, you see there's a couple lines here that are not obvious over here, and a couple here, and they tend to be between these three and those. So probably one of these is that other one, and we can worry about that, or we could decide that we might not be able to see that one very well. It's also possible that we're talking about this line right there, which we can see here quite well, but we can't see very well up here. Similarly, we can see this line here quite well, but we can't see it up here. So these are the lines that we're talking about, and you can see some of them are more obvious than others. Given given what you might expect, what you don't see here, that's clearly the most obvious other one that would be a good one to measure. So let's assume it's that for now, and then we'll see if that actually works out. And because we're going to be fitting these data, if you can't measure something, just don't put them in. Just leave it blank. Now, to try to figure out which one of these lines corresponds to which of these, notice something. These numbers here are kind of 389, 397. They're about 10 nanometers apart. And then these are about 10 nanometers apart. Then this one is 24 from that, and then pretty close to that. So number 4 and number 5, there's a big gap. But number 5 and number 6 are close. So you can see these three, and then that one there, the fourth one, there's a big gap. So it's close to the fifth one, so it's probably that one there. So now we've answered our question about which one it is. That is the faint one. And the bottom line is that's how you do spectroscopy, is you look for patterns, and when you find your patterns in your data, for example, then you can figure out what element that is. So now I'm going to zoom in on one of the ones I can see all the lines of, and I'm going to use this for my calibration. Notice all these pictures are the same scale and at exactly the same place. So as long as we make the measurements the same, we should be good. I don't trust knowing how far this edge is to the first one being necessarily exactly the same. It probably is. So I think I'm going to pick this first thick line here and just make a mark on it, and then call that mark whatever our 0 is, and then just measure from there. It doesn't matter where you pick as the 0, so long as it's exactly the same for all the pictures, and so long as you're consistent. So now that I've made that mark, and I put it smack in the middle of that line, but I made it thin so I can measure to it a little bit better. What I'm going to do now is I'm going to measure from this mark to each of these marks here, and I'm going to write down the measurements. Clearly the measurement from this mark to, well, the mark I drew to this is 0, because that's the way I drew it. That was arbitrary, but I will fill that in as a data point. So here we go. I'm going to make my measurements in millimeters, and I'm going to put a 0 here for 0 millimeters. Now, what should my error bar be? Well, let's go back to the other drawing and see how thick the line is. Okay, you can see that I could put this mark kind of in the middle of this line within a millimeter either way, because it's pretty thick. So I'm going to put in 1 millimeter as my error bar for the first point. Now in practice, our system is going to be overdetermined, so the error can be estimated from making the plot, which is going to be nice. Now I'm going to measure the distance from here to each of these, and as long as you are consistent with units, you should be fine. Just remember that if you don't use millimeters, to change the Excel spreadsheet accordingly. So I'm going to put my 0 right here. All right, and this is lined up pretty good. So this mark here is between 5 and 6. So we're going to call it 5.5. And this is between 9 and 10 millimeters, so we're going to call it 9.5. So I can fill my data in here. 5.5 plus or minus 0.5 millimeters, and 9.5 plus or minus 0.5 millimeters. Now I'm going to go through and I'm going to measure the others and see how they do. Okay, here I go. I'm going to line this up, and I'm going to see what I get here. I get between let's see, 3 point, oh wait, see, this is like 30 millimeters, so it's like, that's 31, it's like 30.7 plus or minus 3. So here we have 30.7 plus or minus 0.3 millimeters, and then I'm going to go and continue doing the rest of them. Notice when you do them, make sure that you line the 0 right at your mark, so it's exactly the same point. Another thing I could have done is once I lined it up, I could have taped it down. That might have been helpful, but I need to pick it up again to measure some of my other things. Okay, now I've filled in all my data after measuring them all in exactly the same way. And now what I'm going to do is I'm going to type them into Excel, and then I should be able to make a plot and find a relationship between what I measure and what my reference wavelength is. Therefore, if I make a different measurement, let's say 33 or something, I know it's between here and here, but I know exactly where it is. And that's a way, that way I can know for any wavelength, if I measure them exactly the same way, then I can find the actual wavelength from my measurement. So again, what unit you use doesn't matter so much. Where you start it doesn't matter so much, but you have to be completely consistent all the way through. This is what's called calibrating our data, and that way we can then use this, we can find, because of the reference lines, the actual wavelength of the lines from the actual galaxies that were observed. So once you've done that, then you're going to eventually want to know what each of these two lines here are. And to do that, you're going to measure them in exactly the same way as we measured the reference lines. So let's use this was an example because, as you can see, we used it before. So I'm going to measure exactly the same way as I did before. That's the key. And you can see it's at 1 point, let's see, 10 millimeters, 15 millimeters, 16, 17, between 17 and 18 millimeters, or between 16 and 17 millimeters. So it's 16.5 millimeters plus or minus about half a millimeter. And this one here is at let's see, between 18.5 and 19.5 plus or minus 0.5 millimeters. So I'm marking those here. And you might as well go through and do that for each one now. And then when you get to the right point in the spreadsheet, you can enter them in. That way it's fresh in your mind how you made the measurements of the calibration source as you make these measurements. Notice this is not going to tell you the wavelength of directly, but once you run the calibration routine, it'll tell you the wavelength, and you know that it's bigger than that wavelength and smaller than that wavelength, but it should give you a much better value. So in short, that's how you make the measurements on the sheet for the spectra. Later in the lab, you're also going to make measurements for the diameters of the galaxies. And all of these galaxies on the left-hand picture are pictures that were taken at the same plate scale. So all of these are at the same plate scale. I'm not exactly sure what the plate scale is. It wasn't clear, but we all know they're the same plate scale. So, and they also picked a representative galaxy that was the biggest galaxy in each one. That's what's called a giant elliptical, or a CD galaxy, and they picked it for each one. So they should be ideally the same physical size. They might not be the same physical size really, but we're going to make that assumption. Now again, the details of how you measure the diameter are less important than that you do it exactly the same way for each one. So for example, for this one, I'm going to measure the long diameter, and like I said, if you measure the short diameter, it's probably okay, just as long as you measure short diameter for all of them. Because what we're interested in for measuring these are the ratio of the angular sizes. And once we find the ratio of the angular sizes, we can estimate the ratio of the distances if we assume that everything has the same physical size. So for this first one on my chart, based on the printout I made, and remember, everybody's going to print it out slightly differently, so you're going to have different numbers when you measure these, but you should come out with the same wavelengths and the same ratio of angular sizes when you're done. So 26 plus or minus 1 millimeters is what I measured it to be. What I did was I just drew the diameter and then I measured it. So for each of the other ones, I drew their diameters so I could measure them as best as I could. And then I'm going to measure right across it, because sometimes my lines might not quite be parallel. Measure right across it for each one. And I should come out with, different measurements all the way down. Notice that, that as you go further and further down the chart, the diameters get smaller and smaller. Therefore, each of these galaxies is further and further away. Okay, so now I have measured, I'm going to zoom out. So you can see now I've measured each one, and you can see how they're getting smaller and smaller. So now I have my measure of my diameters in each of my pictures, and I have filled in my sheet here for my calibration. And then if I go through and carefully for each one measure the distances from the first line to each of these gaps, from what's called the calcium H and K line gaps, first to each of them, and I go through and I measure each of those, then I will be done with my measuring on the sheet, and then I can use those data to put them into my spreadsheet. Okay, so now I've typed in my data from before that we just took about the reference lines, just the reference line data, into one of the first pages of the spreadsheet. And you can see here it says reference line spacing, and I filled in the data just like we talked about. Then you can see it lines up beautifully. You see this is the wavelength and this is the reference line. And you can see the error bars are teeny tiny, and it makes a very good line. That's typical for calibration data. It's not necessarily typical for real astronomical data. Often there's more scatter in that because they're intrinsic things, not just measurement error. And I fit a line here and a trend line. Usually what you do is you right click on it and it will tell you fit trend line. And I have a slope of 1.4057 and an intercept of 391.23. Now you can see the units of the intercept are wavelength in nanometers, and the units of the slope are going to be nanometers per, and this is wrong, it's not pixels, it's millimeters, so we're going to change that. Because remember, we said before that you can make the measurements in either pixels or millimeters, but be consistent. So what you change it is you just click on that and you change pixels to millimeters. Now, the equation of best fit here, I also put a function in, and you can look at that and you can see this is the intercept and this is the error in that based on the scatter. So it's very small. So now if I ever make measurements the same way for something else, I can find the corresponding wavelength just using the y equals mx plus b formula from high school algebra, where m is this and B is this. And I think you can see my cursor now, but I'm not sure. So what we now have is, this is the spreadsheet as I typed it in. These are what I just made, and then this is this line. Now I'll check to see if you can actually see my cursor. Sometimes it's hard to use the software. There's a learning curve. Okay, now I've printed out the second page of the spreadsheet. Notice we have the column letters here and the column numbers here. And I want to show you what I did. I filled in my spacing for the first line, from the first line, and this, by the way, I need to change to millimeters because that was the unit that I used. And then, once I got that, and I put in my errors, I found my wavelengths. Now, how did I do that? I put in here the formula that corresponds to y equals mx plus b. That's how I did that. Now, what's y? Y is the wavelength. M is the slope, and b is the intercept here. So you can see I copied over for you, and you can double check that it's right, the slope and the intercept from the page before. It's good practice when you use numbers from the page before to copy them over so it's clear. Now if you take this and put it there, and you take this and put it there, you should be able to find this just fine. Now, so what you'll put in here, of course, is going to be equals whatever m is, which is B15. Now don't forget to anchor that, times whatever this is, click on it, plus this. So you can see I put in this because this was the cell that m was in. Notice that for all these values, m is the same. So I anchored it with a $sign using like a boat anchor. Then this is going to be different as I go down and different as I go across this way. So I don't anchor it. And then these here, I then again anchor. Because of course this is that cell there, which changes as I fill down. And of course notice that these values here are the measurements of the calcium K line from the first, exactly the same way as we measure them for the calibration. That's the key. Now the next thing I calculate from the calcium K line is the recessional velocity, meaning how fast is it moving away from us. And now, as we discussed in the other video, if you're moving away from the source, so here is the telescope, here is the galaxy, and it's moving that way. The light that it emits has a given wavelength, which we can call lambda 0, lambda 0. But what we catch is not the same wavelength because each successive wavelength the galaxy was further and further away. So what we catch we call lambda. And the ratio of the difference of these to the wavelength emitted is the same thing as the ratio of the speed to the speed of light, or the speed over the speed of light must equal lambda minus lambda 0, that's the rest wavelength, divided by lambda 0. Multiply both sides by the speed of light, and you can solve for v. And this equation is what we're going to put in here, solving for v. So we type in here, we're going to have to look and see which cells things are in. So my recessional velocity v is given by this equation we just talked about. So we put in this one here equals J, $11, which corresponds to the speed of light, times E3, which corresponds to the wavelength, minus $B at $12, which corresponds to the calcium K. You see? Down here, the calcium K wavelength. Notice this is K, and this is K. How do we know that the first one is K and the second one is H? Because this is a smaller number than this. Then, if you go back to here, then all this is divided by $B, $12. Notice how we have to put the dollar signs in so that we can fill these down, and so eventually we can copy them over for the H line as well. Now I want to say something about the error bars here. The way that we do error bars in proportion works perfectly well when you multiply and you divide. The problem is, in this case, we had an addition too. We had a multiplication and an addition. So what I did was I actually put in for this, for the spacing from the first pixel, this plus this, and then subtracted the same thing for this minus this. And you can see that the b's would cancel out if I did that. And so you just get the error times this is what it eventually comes out to be. So it all came out to 1 nanometer for everything when I did that. This here, I was just multiplying, and so I could do our error bars in the same way we've done all semester, which is this times the ratio of the error to the quantity, and you can add those up. Now, if you look at the last sheet, here are my image diameters, here's my distances to the galaxies, and here are my velocities. We just discussed how you find the distance to the galaxies. Now, notice something about this, is that when I plot these up, there's a beautiful relationship between the distance and the velocity. Notice what a tight correlation this is. Now, how good of a correlation that is, depends on how many galaxies we have, and also there's big error bars in the distance to the galaxies, and you can see especially as we go further and further away. So, in this case here, we made this plot. I fit a best fit slope to my data, which turns out to be about 98 plus or minus 31 kilometers per second per megaparsec. Slopes have units again of whatever the vertical axis is divided by whatever the horizontal axis is. And then to figure out the implied Hubble time from the slope of this, what I did was I said, oh, I know that 14 billion years corresponds to 70 kilometers per second per megaparsec. Why? Because that's the modern value that we have now. Okay, so I know that the current value is this. I also know that this is in units of inverse time, because that's a unit of length and that's a unit of length. And I also know that the faster the universe expands, the younger it implies it is. So I know that the Hubble time is proportional to 1 over the Hubble constant. It's actually equal to that if you work out the units correctly. So I don't have to deal with the units. I'm going to say the Hubble time divided by 14 billion years must equal 1 divided by the Hubble constant divided by 70 kilometers per second per megaparsec. And then therefore that implies that the Hubble time is equal to 14 billion years divided by h over 70 kilometers per second per megaparsec. So what I put right here is equal to 14 divided by this cell here, which looks, I just click on it, I think it's C11 because of the way, because I think it's the first one when you merge them, divided by that cell there, divided by 70. So now that ratio, this divided by that ratio, and I got 10 billion years. So what I get is something a little bigger than the modern value for the Hubble constant, and I get something a little less than the modern value for the age of the universe. This was typical for most of the 20th century, pretty much all the 20th century, is that people who measured the Hubble constant were consistently getting numbers around 100. And the problem was that people who studied stars were getting ages for stars that were more than 10 billion years. And the problem, therefore, was that the stars appeared to be older than the universe, and that was a problem. We now know that the universe is more like 14 billion years, and that the stars are actually a little bit younger, more like 12. So then that's the end of the lab. The whole point of the lab is to find the age of the universe, and we measure the spectra, and we measure the sizes of these galaxies to do so. Okay, thanks.